You guys might find this of interest. Here's the person's name. I think he's has a doctorate, working at FIU, Florida National University, and apparently one of his students um, came up with this test. There's no audio besides music, so let's go ahead and let it run. You might be able to hear breaking, but that's not going to be too helpful. I'm going to change the speed at one point. You're going to be observing, I believe, the same dimensional truss, one in a solid member like this, and one outside, set at 45 degrees from each other. Here's 45 degrees here. When I'm going to let you know now, the load's applied here between the two at the top of the, at the center of this, wall. Because even though you see lines, it is not a truss system. You're looking at really shear break, a load applied to center of a wall, and shear being taking place. I believe the sensor's intent are to monitor it forces, but if this was a solid system, how it would react just with these dimensions. It's going to split this beautifully. It's going to shear it in a fractal way, in a abrupt way. Oh, I think I already have the speed down. Yeah, I've got it at 25. I'm going to leave it there. You guys can come here and watch it at full speed if you so wish. That's the hydraulics going. So it appears this is a 4 by 8 sheet of plywood here, and then half again, and then not quite a 4 by 8, maybe 3 more feet. So maybe this is a total of about 7 feet. Their dimensions are not very clear. So the strut and tie method, STM, is a way to design reinforced concrete structures. In this method, a concrete member is modeled as a theoretical truss or collection of actual loading elements made of a compression member, struts, tension members, ties, and the points where they intersect, nodes. This video shows the results from 2 experimental tests on concrete struts. The rectangular beam has tension in the strut. Okay, so rectangular beam, yeah. Tension in the strut introduced by beam bending that decreases the capacity compared to the truss-like specimen. The rectangular beam has tension in the strut introduced by beam bending. The testing was completed at Florida, and as the PhD student on the project was this person. Thank you also to Gary. So the tension down here is where they're applying the tension apparently across these bars. I sort of did something like this for you guys with the metal, and I left the middle part out and I just applied the load at the top. But this has a compressive moment also. Here we go. I guess I will let it. Isn't that amazing? So it apparently released itself at the bottom also. But look at the top here. How part of it, the forces did not start going on a 45, if you will, until recessed about the same depth of this plate. I wish we had more data on why it chose to start below there. Is it the plate thickness? I don't find this. I find this awesome information, but they don't share. You know, they didn't go down that path. They just were so concerned about the end results of the failure, whereas I'm looking at it as, well, when did the 45 start? I always find these 45s almost always never starting at the very top. They always start somewhere down into the beam and then directional. I don't see any reinforcement or anything else. Looks like a beautiful piece of concrete, and let's move on. I'll give you one more shot at that. Isn't that beautiful? Isn't that beautiful? So there's your explosive moment. Look at all the forces released and the hinge effect again. These hinges, man, they take place. This is not a freebie. You don't get to just break free and call it a day. The greatest force, I believe, is at the closest where you're applying the force. The least is here. This creates the most punching, if you will, punching force. I don't mean punch out. I mean like the forces, if you can imagine them. That this is and this is why it's able to rock this thing's world. All that concrete up and out, literally hinging it, rocking it. Beautiful, beautiful. I'm not going to count too much as hinging on it. Now let's go to his next testing. But also note that it did pick a side. It picked a side, so perhaps his beam wasn't centered just perfectly. Everything's equilibrium. You get nothing for free. If it's down this side, it's because of a reason. It's not random. Nothing's random. You toss a coin up in the air and it comes down a certain heads or tails. Your guess is random, but the outcome was already determined based on the flip, the momentum, everything. We just don't know the outcome until it's done. We're gonna run it again. This is 1 minute 48 5 seconds. I'd love to know what the strain gauge is read. Now this is their slower speed. This is their slower speed. Again, its failure is 557 kips. Wow, look at that thing go. And it's just hinging. I'm saying hinging because there's no reinforcement in here. So if the forces were awesome at the bottom here, clamp force, then it would have just broken it and it was slidden down. It would have slid down the ramp, the created ramp. I think it's beautiful. Look at that break. I mean, it's just beautiful. It's just beautiful. Now let's talk about the break. Wish I can get a little closer to it. But the proportions that he has at this break is not, it's a clean knife. The forces are besides that shelf thing going on there. It's a clean knife all the way down. Total equal loads all the way down, but higher here. And when it finally fractures, the forces might be reversed coming up to create this explosive moment out. Like a rebound, like a rubber band, if you will. But it's beautiful. It's beautiful. That table, I call it the table, the surface. It's just absolutely beautiful. I don't know if there's some what that is, material that's breaking apart and coming down, or is it no. It's just beautiful. Wish we had more. No, it's sliding. Yep. Yeah. I mean, that is just awesome. Never seen anything like it on the sampling. The student is awesome for doing it. Wish we had the data again. So that's 557 kips. Now, it still is intact, but they're going to show the next member when they do this, and it's going to go at 5 something or 4 something, whatever it is. Well, this broke free of its location, but it didn't fail in the strut member. Oh, diagonal tension triggers shear failure. Diagonal tension triggers the shear failure, which I was describing to you. It's just beautiful. And it's equal. That's what I'm saying, though. It's totally equal up there. Not a peeling off, not one side greater than the next. It's just all the way equal. It's just like a huge clamp came down from 2 sides and just sheared it from 2 directions, but fast, very fast, and it had no time to rip. Really doing some liberty there, the rip, if you guys can imagine it, when I did the bolt videos, how you can see the table and you see the tearing, if you will. We have no tearing. We just got clean edges. I mean, this is friggin' just awesome. I mean, I am putting it in relationship to, if you guys ever used a brick breaker, it has two sides, like a guillotine. This is just what it looks like. I would love to know what the force is down here. But again, this is still in place. So even though it's 557 kips at this failure, it still would, if you configure this to work on a bridge, you would have it. I love the redundancy that I think of is you make a shelf. So if this failed, it would drop down to the shelf, not just fail, period. Now, this is 717 kips, but we no longer have the luxury of the other detailing. Um, what's going on here? I don't know. Is this one of the broken pieces? And then they took liberty and cut the other side with a saw. They're not stating how they came about this, but this doesn't appear to be, we're not getting the whole thing. February 23rd, 2017. Well, doesn't it seem like this would be before a bridge collapse of 2018, that this would have been some sample testing of this bridge, that what we have in place? And this would be the canopy loads. Doesn't that seem that way to you guys? But the angles are just wrong. Here we go. It's not, okay, there we go. So we got the meters on again, meter's still present. It's beautiful. Now this is going to fail in the nodal area. The whole area is just going to equally combust. I like that wording. I just made it up. Although, does that already look like it's got part of failure to it? So it would seem like this side would fail first and then the other side. In fact, it already looks like we got some delamination going on here. This appears to be an unreinforced structure that they're working on. Structure as in design. Oh, excuse me. Boom. Okay. So they crossed each other. They broke. They took a rotation. And take note, they crossed each other. This is mostly in place. You got the plate that's gone now. And here we go. And as you zoom in, you see what appears to be possibly a piece of reinforcement across it. And maybe in here too. But let's run it again, Sam. Oh, now this might be that piece. So they confined it this way. They've got the load going up the top there. And go ahead. You can't extrapolate too much from this based on the bridge thing, or you just want to do extrapolation at that point. The angles are the same, not the same. It's confined. It doesn't have ability to move out. It's just not the same. You can extrapolate what you see with this configuration with these materials. There we go again. What do you notice? Oh, what do you notice? That the forces resolve themselves each time at the top of this member, not at the base. Not at the base. That equally they pushed back from pushing in, and I'm going to stick with that. And the cross section up here was obviously not strong enough. We just saw a shear break happen a moment ago, and my guess is that load coming down created a shear also inside this, but there was nothing to split down, so it was able to defeat itself all with up there in this nodal area. 717 kips. Run it again, Sam. Run it again. Okay, this is the same one again. Background here, we got 323. Test number whatever, 2. Thrust, load, 250 tons. 250 tons, 500,000 pounds. We got 717,000 pounds. We got 250 kips, rather. 250,000 pounds, which would be 125 tons. So I have that wrong. Sorry. I zoomed in and I can eat that. I dropped the ball on that, but this is not. We're at 1,700, 17, whatever. Oh, 717. Also very important, since you have a photograph of the debris, this would also tell you the angle of the forces. It appears this is out of level. Most of the forces come this way, so it doesn't appear to be that direction behind it also. So a little rotation, I believe. I play around, guys. I can hit a nail. You can stand a nail up, and I can hit the nail anywhere I want to hit it just by clipping it in the direction, pointing that way. Don't cross the nail in a certain angle, and it will go in that angle when you hit it. It shoots off right towards that angle that you've clipped it at. Same thing here. So this would be the explosion. The clip would be from behind coming this direction. In this case, it looks pretty kind of equalish. So, but I'd say more to the left. Okay, so you're gonna run them both at the same time. This is a split image. This is the same location, and let's let it play. There's not two of these running at the same time. There's two videos running at the same time. So here we have the brake, but this is still in place as I stated. And here we are. So I wouldn't know what, they should keep loading this to see when it, reclamp it. Keep loading it, see when it fails. That's my thought. But I want to send you guys over here, and then FIU is still not over themselves about being the world's greatest bridge builders. They're not over themselves. If we troll over to my man's channel here, and I got nothing against him at this time, we have the 2019 Parent-Child Bridge Engineering Camp at FIU. Here is the guy to the right, their doctorate's guy, and that's the Gerber guy. I think we just saw a Garber. And that's the engineer guy, their head doctorate's engineer guy here. So I find this quite telling, to say the least. And that appears to be the same guy here running the test. Want to get to failures. Watch these guys, have a little fun, see what you can see where you can fail. You can basically see that, you just look at the design, pause first, and you can see where it lacks uniformity. It's crowned here, down here. So you would think somewhere around this area is twisted. That would be the failure, and that's where it comes out to. I guessed every last failure of this one. Fast forwarding. 2 times. So that was the beginning and their ultimate. And then it's interesting. I watched that over and over again. That was the one I actually watched over and over again. You watch it take a redirect. Let me show you. Your initial bend is here. But then, as the bridge is failing, it twists and the next break in the air is right about there. Right about there. So your first is here, now here's your second. And then back to that point again. Right there. There's your hinge. Well, they were all doomed to fail. These tests are always designed to end in failure. This one is, they're kids, right? Look at the shape of it. It's an interesting shape. I kind of liked it. I thought if they do it over here again, tall truss, and short truss, you might get a little something going on. This was interesting. I'm not going to give away, since I already watched it and I know where the brakes happen. I like this kid that kept working on trying to get it across the bridge, though, the little car. I'm going to terminate the video. You guys can come over here and look at it. Look up David Garber here. He's got a good program here, reinforced concrete. But isn't that something? FIU dealing with Child Bridge Engineering Camp. Really? All right, take care, guys.